Hello. Hey, everyone. My name is Soumith. I work at Facebook AI Research. We, at Facebook AI Research, we basically are trying to, like, our single goal is to solve AI, and we work on very long-term fundamental research for AI. So today I'll be talking about a class of neural networks that we recently built called deep adversarial networks, and let's get started. So the overview of the talk is that I will talk a little bit about the problem at hand with a simple use case, and then I will also go over how we solve it, and then I will talk a little bit about our research and publications in this area, and somewhere intertwined between all of these, I'll be talking about the benefits of what we built. And all right, let's take a simple problem. So you are sitting on the corner of 8th Street and 5th Avenue, and you want to walk a couple blocks to eat some pizza. This is pretty simple problem, right? You basically want to you want to plan your route. You want to walk 2 blocks up and 1 block east or something like that. So you basically ask Google Maps, hey, how can I go to this place, Patsy's Pizzeria, a couple of blocks away, and it gives you one route. The first route it gives you is it's a 4-minute walk, pretty straightforward. You walk a couple of blocks up and then walk a couple of blocks east, and it's there. Then it gives you alternative routes that you can take just in case you don't want to take the first route. And the alternative routes are equally enticing. They're about the same. They take about the same time. Now, what you can think of Google Maps here when you're asking it for routes is it's some kind of a route generator. You give it point A and point B, and it's giving you all the possible routes that you can take within some bounds of common sense. So if you think of this as a machine learning problem, like let's say you want to build a robot or an AI, like if it wants to do a task A, it needs to plan how to go about doing it with sub goals and plan all the steps like that, break the task down into smaller steps. So for planning, the agent needs to know what happens if it takes a particular action, and you can look at this route generator that Google Maps is as something that helps you plan your tasks. And so we would want to, in this, because you want to basically do planning and you want to learn about the world by basically walking around and taking routes, you want some kind of route generator that you want to train for your agent that basically takes a point, that wants to go from point A and point B, and it generates all possible routes. So the training data for this route generator is let's say initially the training data is given by Google Maps itself. It's basically the top 3 or 4 maps, the routes that Google Maps gives. That's your training data, and now you're just trying to mimic Google Maps here. So you basically have this black box, a route generator. Let's say it's a standard linear regressor. But instead of taking in point A and point B and generating a single route, you want it to also generate a bunch of routes. Like you want to let the routes have variability. So you have some input noise that basically, as you change the noise, you will get different routes. That's the purpose of the input noise. And then the output of this route generator that you train is the route itself. So you change the input noise, you get a different route every time. So to train this thing, you need some kind of optimizer. So we'll take a standard cost function, like the mean square error, that measures for each route that you generate when you're trying to improve yourself. It measures the route that you got, the exact distance, the L2 loss between the route that you generated and the routes in your training data. So essentially, you're trying to mimic the training data as simply as possible. So what could go wrong here? So you have your training data, and you want to build a route generator. You pose this as a standard linear regression problem with a mean square error loss. Well, this is what could go wrong. Like, the route generator will basically give you a route that is just going through buildings through the center. It's like, well, just take the average of all the routes. That seems like a great route. It seems really fast to go. The problem is that, and you sample more routes, it's essentially going to give you, it's going to give you things around the mean of your distribution. This is a problem because it's not aware of what a plausible route is and what a plausible route is not. So yeah, you're sitting there, you're like, what's going on? And the problem is that your routes, the problem is that you're converging to the mean of the distribution, and what you want instead is some kind of route validator. So let's try to build this system again. So if we build this system again, then you have a route generator that takes in some noise, and then it takes in point A and point B that you want to go to. It produces a route, and then you realize that a mean square error loss is actually a terrible idea. What you instead want is some loss that measures whether it's a valid route or not. And how do you go about doing this? How do you construct a loss that says, okay, this given route is valid or this given route is not valid? That is a hard problem. Well, for a route generator, it's probably not that hard. You could probably be like, well, I will just check if the route is, I'll write a complicated loss that's like, okay, is the route going through buildings? Are there collisions with buildings? Or you could write some very complicated loss that takes up like 100 lines of code or something. But if you think about generators in general, like, let's make it more generic. Like, let's forget about the route generator. Now you want a generator for some task that takes in some input training data, and it needs to generate samples that look similar to the training data. The problem there is it's not very obvious how you construct this for every new task. For example, if you want to generate a natural image, you want to basically say, okay, here's my model, it takes in some noise, and it has to produce some image of the world, some picture that I took, or some picture that is possibly from the world. Like, how do you validate this? You just, like, to write a loss function that validates this is super hard. Like, you simply can't cover all the cases that are possible. Another example is if you're like something that we as humans do very every day. You, as a human, you predict what's going to happen next in terms of like your visual sequences. Like you have like, let's think of it as video generation. You have the last 4 or 5 frames of what happened, and then you want to predict what's going to happen next. Like if I throw this thing at one of you, before it reaches you, you know that it's coming at you. You predict that it's coming at you, and you duck. Like, this is something we do standard every day, and we take it for granted. So how do we learn, how do we build this cost function? One way is you also simply learn the cost function. which is what you do is, oh, there's a little bit of lag on this. Give me a second. Okay. All right. What you do is you just like you have a generator that takes in your input noise and it produces some sample. You also have another learned system, the discriminator, that basically takes in a generated sample or a real sample, and it has to be able to tell whether it's real or fake. Now it becomes a simple classification problem at the end. The loss itself is fairly simple. There's a lot of literature here. Everyone here does this in their machine learning system. So you can basically build these, make the generator and discriminator be neural networks, just standard off-the-shelf neural networks. And you can train them via gradient descent, nothing fancy here. And the way you train them is that when you're trying to optimize the generator, you optimize the generator to fool the discriminator. That is, like, the generator has to generate a sample that the discriminator can't tell between real and fake. That's basically what it's optimizing for. And when you're optimizing the discriminator, you're basically like, well, don't get fooled by the generator. Like, try to optimize yourself to tell real samples from fake samples. This is a very, very intuitive block system here, where it's just an alternative optimization, a minimax problem, and you can build very complicated metrics on you can build learned cost functions here that are very complicated that you wouldn't build by hand. And we as humans take these, like, we do this all the time. We can tell real from fake. I mean, we just do that every day. So while waiting for my next slide, all right. Sorry, it went two slides. Okay. So this method was proposed by Ian Goodfellow and his colleagues in 2014 December at a conference called NIPS. It was from a historical perspective, this is a model that Ian came up with in a bar in 10 minutes while he was having drinks with some friends. And then they wrote this paper in a couple of weeks, did some experiments and so on. It's something that happened on a whim, but once you look back at it, it's like, well, this is a very cool model that we should have thought of. It's a very obvious thing to do. So in their initial paper, what Ian and his colleagues did was that they tried to model what I said was a very hard thing to do, model natural images. You want to basically have a generator that generates natural images. It takes in some input noise and just generates some natural images. And if you look at these, they don't look very good. But these were actually awesome for when they were generated. It's like all the generative models we had before that generated natural images, they sucked. And this is a very hard problem. And just to, as I said before, having such generative models on very complicated distributions help you do better planning. You can do Monte Carlo tree search on all the future possibilities. Now you have a distribution of possibilities and you can choose between what to do next. So after Ian published this paper, I was at the conference and I was like, wow, this is really cool. And then I went and implemented it. And we were thinking about how to extend this to not suck. One of the problems with this model was that it generated images, but there was no guarantee on whether it was not a conditional model. It just took the noise as input and then it just generated an arbitrary image. Going back to our root generation problem, you could, if you train this model, it could generate some other root 4, that basically goes to the Bronx Zoo and comes back. Now you want to go 2 blocks down, but it's like, well, this is a valid route. Why not? So this, the generative model didn't have a notion of what is a good route or not. It wasn't a probability distribution where you could basically sample from the higher density, more plausible routes and not sample from the less plausible parts. So what all right. So what we did 6 months after that, or 7 months after that, is we built a new model that we published at NIPS the next year, the same conference in 2015. And instead of just taking noise as input for your generator, we also take your the class that you want to generate. So let's say let's say you're still generating images. You can also send in as input the class of the object that you want to generate. Let's say you want to generate a ship. You give a categorical distribution as your input, where you put a 1 at the ship part of the distribution and 0 everywhere else. And the rest of your model stays the same. You don't even add to the cost function anything to do with generating classes, for example. And this worked really well. So with the same model, when you ask it to generate airplanes, it generates different airplanes. When you ask it to generate automobiles, it tries to do that, and so on. It basically was a class conditional model that still generated very complicated distributions, and it you could tell it what to generate, and you can see how this would be useful. It's like now you can do your route generator that takes in as input point A and point B and actually generates routes for that particular generator. So in this case, we have the question was, how do you find the class input? In this case, we had a supervised data where you had images and you had their corresponding classes. So this was what we called the LabGAN model, and we also had other things that improved the GAN structure. We had a Laplacian structure that would let you build more and more complicated models, and if you see, these images look much better than Goodfellow's original paper. So all of these improvements and the class conditional was one thing that we progressed at. So the next thing that some of my colleagues did that I want to talk about, but I'm waiting for is, so the next thing I want to talk about is the other hard problem that we do every day that is very hard for machine learning models, which is like video prediction. You take in the past X frames and you want to predict the next Y frames so that you can plan according to what you think happens. And traditionally, what people used to do was they used to take the past X frames and then they used to generate some frame, and then they used to take the mean square error between the generated frame and what you had as ground truth. And what ended up happening was that you always got really blurry samples. Like the video that was, like the frames that were generated were just blurry. And it's the same problem. The generations were regressing to the mean of your distribution rather than actually giving you one plausible path. So in this paper, what our colleagues did was, instead of just having a GAN that had a generator and discriminator, and the discriminator would tell whether the predicted video frame is real or fake, it would also have the standard mean square error laws that were used traditionally. And the reason this is done is because if you go back to the route generator example, the fourth route that was that basically took you to the Bronx Zoo and back, that fourth route could be avoided if you have this mean square error loss. Basically, you're combining both methods where you say, I want a plausible route, but I also want a route that is close to my training samples, where I have plausible routes and not just like arbitrary routes. So some of the results I want to show in the paper they published are coming up in the next image. And okay, so you have 4 input frames here that you are given. This is and these are, the videos to this system are very random. Here I just took an example of you have on a billiards table you have a video running. You have the 4 input frames, and you want to predict where the balls go next. You want to basically predict the frame. And so if you see on the top right, if you have a standard L2 loss, that is the mean square error loss, you see really blurry samples. Basically, this is what people have been trying to use when they do generative modeling forever. And the blurriness is just like, it's bad. It's not even a plausible frame predictor. So on the bottom right, you see what comes in with the adversarial, just the purely adversarial net, and also the adversarial plus this mean square error kind of loss. You start actually predicting what happens next with reasonable plausibility, and they're also close to what would happen next in your training data on average. So this is great. Like if you have this, now if you have like a video with like something that generates the future, then you could be like, well, I kind of in my head know where the balls are going. So like, I mean, this is how you play billiards, right? Like before you even hit the shot, you do a bunch of possibly, like you say, okay, if I hit it this way, the ball is going to go this way, and then go to that hole there that I want to put it in. So if the machine learning model or the AI agent that you're building has this model internally, it can plan way better. It can basically look at all the possibilities and plan for the best outcome possible. And finally, the last paper I want to talk about is this paper that we recently published. It's going to appear in a conference called iClear in about 15 days. Like the problem with all the previous work was that, I mean, everything was going great except that we couldn't scale up these models to larger and larger images, or like more like the images weren't just plausible enough to fool a human himself. Like in the LabCan paper, for example, we ran a human study, and it would only fool humans. The generated images would only fool humans 40% of the time. The rest of the 60%, a human could easily tell the difference between real and fake. And so we wanted to basically do some model search, try to predict better try to build better models that would capture this complicated task of generating images. And so we found through a lot of model selection and carefully choosing things, we found a certain class of convolutional neural networks that are really stable and perform really well for generative adversarial networks. And these images that you're seeing here, they're generations of bedrooms, and they're all fake. Like, they're basically generated bedrooms, and some of them you can't tell from if you're given the same image and say, oh, this is actually a real bedroom. Like, and this was a big deal, because for the longest time, image generation was like a hard problem that we've tried to tackle for a long time, and then now we're here where the generations here start looking really, really good, and now you're plausibly fooling a human. And one thing we wanted to do with this model was that now that we have the generator and discriminator, can we just use the discriminator? If you think about this problem, it's an unsupervised learning problem, right? Like you basically you have a generator and discriminator. The only label you have is whether it's real or fake, whether the images are real or fake. Like you don't have hard labels on like whether it's a particular class or there's nothing as a human that you hand labeled. So what we did was we took the discriminator that we trained from the adversarial network, and we used that as a feature extractor, standard feature extractor. And we just trained an SVM on top for a task that is in Google Street View. If you want to identify house numbers, then there's a lot of research on doing that, and there are data sets where like you have a bunch of street view images with house numbers and you have to predict what number it is. So we took that data set and we limited the data set to just 1,000 labels, that is 100 labels per class. And this is a very limited amount of data for what you're trying to do, because your neural network itself has like millions of parameters. It's just, if you just have 1,000 labels and you train it from scratch, it's just going to overfit to the training set. It's never going to perform really well on the test set. So we took the discriminator, used it as a feature extractor, just used 1,000 labels, and our system got 22% error rate. It did really well 80% of the time on this 10 class problems, just with 1,000 tables, even though it had millions of parameters. This seemed awesome to us because this neural network just learned a bunch of features of the world just by playing this game of adversarial networks. And another thing, by the way, these faces here, they're not real. They're just generated samples. Another thing we did was like it learned features such as glasses or smile, etc., without having to, just by playing this unsupervised game. So to conclude, unsupervised learning, the GANs really help with unsupervised learning, and they help with planning. And they seem to be really powerful models, and we are doing active research to use them. So